Hi, everybody. What we're going to talk about today is polynomial functions. So, a couple little reminders for you. The degree of a polynomial function is the greatest exponent of its variable. And of course, you know that the lead coefficient is the coefficient of that term that has the greatest variable. So sometimes we're given a function and it's not written in descending order. So we're going to write this in descending order, and we do that by exponent. So this term has the greatest exponent, so we would write that one first and kind of move on down the line. We have minus 5x to the third. We've got this right here, plus 2x squared, plus 4x plus 2. And a couple things you need to know. The 3 is our lead coefficient. The 4 tells us we have a fourth degree polynomial. And just a reminder that the 2 right here is our constant. And what we're going to be graphing are kind of functions that look like this. But what we know is that this is our y-intercept, just like how it's been our y-intercept for y equals mx plus b, or the quadratic functions that we've done so many of. Okay, so let's move along. And this is just a little refresher for you. Remember, when we're doing a problem like this, where it says, calculate f of negative 5, all we're going to do is take that negative 5 and substitute it in. So when we do f of negative 5, we do negative 5 cubed. That's one you should know, negative 125, plus negative 5 squared is 25, plus 4 is 100, minus 2 times negative 5 gives us plus 10. And then, of course, plus 6. And we see what that all shakes out to be. When you calculate everything out, you should get that f of negative 5 equals negative 9. And what that represents is important. It is the point negative 5, negative 9. So we can also substitute in with a variable, and we do that the same exact way. So we're going to substitute in with 2a, not like 2a from quad form, just 2a. So I don't know, maybe you want to write this one out. You can always do this. And go ahead and maybe stop the video and see what you get for this. Okay, how did you do there? Check those coefficients, make sure you're squaring things when you're supposed to. Like, for example, here, you had to square the 2a first and then multiply by 4. Don't forget your order of operations and your PEMDAS. And a little bit more complicated here. I gave you a lot of room for this. We're going to substitute a squared plus 1 in here. What I would recommend, because we want to make sure that we FOIL, is that you write this one out. A squared plus 1, and then plus 4 times a squared plus 1, right? Everywhere we see an x, we put a squared plus 1 plus 5. So again, what I'd like for you to do is pause the video. Go ahead and do this. You're going to have to do some FOIL. You're going to have to do some distribution and then combining like terms. And let's see if you get the same answer as me. Pause the video. Okay, check your answer. See how you did. Okay, we had some squaring to do here. We had some distribution to do here, and then combining the like terms. Okay, so this is just how we express a polynomial function. We always go in decreasing order, so n being the first, the greatest exponent, n minus 1, and so on down the line until we get to that constant. Okay, and as we talked about, the constant is still going to be the y-intercept, even though we're going to be dealing with some more complicated polynomial functions. So this is an example. Okay, so basically, when we are dealing with polynomial functions, looking at the greatest exponent will tell us the overall look of the function. So let me give you a little information here. First of all, a linear function is first degree, okay? So degree equals 1. That's just going to be a line, okay? That's just going to be a line. So that's a line with a positive lead coefficient. I'm going to put a plus up here. And maybe we'll do 2 different colors here. And this would be a line with a negative lead coefficient. Okay. For the second one, a quadratic is degree 2. That's like y equals x squared or y equals x plus 2 squared minus 7. Okay, so for degree 2, it's just going to be x squared is our largest exponent. Positive lead coefficient is going to look like this. Okay, and we know the negative lead coefficient reflects it. So that's our negative lead coefficient. A cubic function is degree 3. And we've done those as well when we did families of functions. Okay, positive lead coefficient looks like this. Starts low, ends at the top. A negative lead coefficient reflects it, so it starts high and then ends going down low, low, low forever to infinity. Okay, so now we're going to get into some more that you haven't done yet. So a quartic is a 4th power, okay? So degree 4, if we want to look at it that way. And a 4th degree polynomial looks like this. It has four directions in the graph. So look, 1, 2, 3, 4, something like that. And that's a positive. Notice that with the positive lead coefficient, these two both end where both sides are going up. Okay, and with a negative, it would look something like this, where they would both be going down forever and ever and ever to negative infinity. That's going to be important for us to know. A 5th degree polynomial, okay, is called a quintic. Okay, so again, degree 5, I know it says it there, degree 5. And that's going to look like our 3rd degree polynomial with an extra term. So starting low and going 1 direction, 2, 3, 4, 5, something like that. And that is a positive lead coefficient. If it had a negative lead coefficient, it would be reflected. So it would look a lot like this one over here with an extra bump in it. So down, 2, 3, 4, 5. And that would be having a negative lead coefficient and a 5th degree polynomial. So something like y equals x to the 5th plus 2, or y equals negative x, 2x to the 5th minus plus 5 minus whatever. Okay? And then our 6th degree polynomial, it's going to look like the 2nd and the 4th with an extra turn in it. So starting like this, starting from the top, it's going to go down and then turn 3, 4, 5, 6, something like that. And that's what a positive 6th degree polynomial function would look like with a positive lead coefficient. And you can probably guess by now the reflection would happen. So 1, 2, 3, 4, 5, 6. That would be a 6th degree polynomial function with a negative lead coefficient. So some patterns occur here. 1st, 3rd, and 5th degree polynomials. I want you to notice we have one arrow going to negative infinity, one going to positive infinity, right? Even when we reflect it, the end behaviors, which is what we're about to talk about, are different. One goes forever to negative infinity, one goes forever to positive infinity. If you look at the 2nd, 4th, and 6th degree polynomials, think of the parabola as the easiest one. Both sides either go up or both sides go down. Same thing for a 4th degree polynomial. They're going to infinity or they're going to negative infinity. And same for the 6th degree polynomial. So I've already alluded to this, talked about the end behavior. So the end behavior basically is the direction that the graph goes as, like the height that the graph goes as we move either to the right on our graph to positive infinity, or as we move to the left on our graph as x approaches negative infinity. And there's a very specific way that we write this. So I'm going to do the first two with you, and then you'll do the next two. So what we say is this: we can clearly see that as we move to the right on this graph, our function is decreasing. So what we will say is, as x approaches infinity, we write it like that, f of x, remember f of x is just the height of our graph, approaches negative infinity. And then we do again, and now we say as we go to the left on our graph, f of x goes to negative infinity. So we say as the x value goes to negative infinity, in other words, becomes smaller and smaller and smaller, it moves left, f of x also approaches negative infinity. I'm going to put little arrows on this. This graph doesn't have arrows. Okay, let's look at the next one. By the way, 1, 2, 3, 4, fifth degree polynomial. Okay, and what we can see is as we move to the right on the graph, x will go to positive infinity. It'll get bigger and bigger and bigger. So as x approaches infinity, f of x approaches infinity. The height goes up forever. As we go to the left on the graph, you can see that we're going down, 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 down forever. So as x approaches negative infinity, f of x approaches negative infinity. So what I'd like for you to do, as you probably figured out already, I would like for you to pause the video and go ahead and see what you can do about these two functions and writing their end behaviors. Okay, and keep in mind these really should have arrows at the end. So go ahead and pause that video, write your end behaviors, and then start the video up and see if you got them right. Okay, so take a look at how you did. I know automatically, because these two are going in the same direction, I know that this is an even degree polynomial. In other words, the greatest exponent of this polynomial function is an even number. And I know, because these are going in opposite directions, that this is an odd degree polynomial without even counting all the directions. This one, 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. And we can obviously see our end behaviors, and hopefully you did okay on those. Oops. So we can summarize all of this. Okay. We can summarize all of what we've been kind of talking about based on whether we have an even or an odd degree polynomial and what the lead coefficient looks like. So if we have an even degree polynomial with a positive lead coefficient, think about a parabola right now. It would look something like this, or it might look something like this. So what we know about the end behaviors is that they'll both be going to positive infinity. So we can say as x approaches infinity, f of x approaches infinity. And as x approaches negative infinity, f of x also approaches infinity. They both go up forever and ever and ever. Zoom this so I can. Okay. In terms of an even degree polynomial, so again, think of y equals x squared. If we have a negative lead coefficient, it's going to look like this. Or if it was fourth degree, it would have an extra little bump in there, an extra little turn. So both are going to negative infinity. So as x approaches negative infinity, infinity, we usually do that one first. F of x approaches infinity. Negative infinity, sorry. And as x approaches negative infinity, f of x also approaches negative infinity. What we're basically saying there is any even degree polynomial with a negative lead coefficient is going to have n behaviors that both go to negative infinity. You're going to have to memorize these, by the way. But if you can always think back to the quadratic, right? The parabola that you're so good at, that might help. Okay, so now we're going to deal with an odd degree polynomial. So think about y equals x squared. I'm sorry, x cubed. Y equals x cubed. Or y equals 2x plus 5, right? That is just a line. We know if it has a positive lead coefficient, it's going to look like this. This goes way back to families of functions, doesn't it? And our line would intersect here and have a slope of 2. It would look like that. What do you notice about the n behaviors? Hopefully what you notice is that they're going in different directions. So as we move to the right on our graph, our height increases. So as x gets bigger, right, approaches infinity, the height of the graph goes to infinity. It's going up forever and ever and ever. As x approaches negative infinity, so as you're moving left on the graph, the height is going down. So f of x approaches negative infinity. If you can do the even, if you can do the odd positive, you can do the odd negative, because now you're just thinking of this, okay, which reflects our functions. So that's odd negative. That's a third degree polynomial with a negative lead coefficient. Here's a line with a negative slope. So y equals negative 2x plus 9. Looks like that's what it might be. And if we look at that, we can see that as x approaches infinity, we're going down, down, down forever and ever. So f of x approaches negative infinity. And as we go to the left on our graph, so as x approaches negative infinity, as the x values get smaller and smaller and smaller, what happens to our height? It's going up. So f of x approaches infinity. Okay, so you're going to have a little bit of memorizing to do with this for sure. You definitely want to think about what these functions look like. You know, if you can picture them, if you can have a go-to function like the quadratic for these and the cubic for these, then maybe that'll give you an idea of what they look like. And then that would be the same for any of the odds with the functions that I have on the screen right now, or the even degree polynomials with the functions that I have on the screen right now. Okay? Have a wonderful day, everybody.